I'm Célestin. I'm working with the University of Rwanda, Department of Mathematics. So I have been working with regroup analysis of differential equations, specifically group classification problem of differential equations. Today's talk is based on my research paper, which has been published recently, and it has the title Equivalence, Groupoid, and Group Classification of Multidimensional Non-Linear Schrödinger Equations. Multidimensional non-linear Schrödinger equations are a type of PDEs, which are very interesting in mathematical physics area, especially in quantum physics, quantum theory, Bose-Einstein, and so on. Here is the outline of the talk. We'll give you the background and motivation, and then we'll talk about the definitions, and then I will come back to the statement of the problem, and then I will go deeply with the group classification of the multidimensional non-linear Schrödinger equations. And then I will come back to the results and then to the conclusion. Generally, the analysis of differential equation according to their symmetry properties started in 1874 by a mathematician called Sophus-Lee. A symmetry of differential equations, it is an invertible transformation that maps any solution of differential equation to another solutions of the same equation. So it preserves the solution of differential equations. In the application of the symmetry, so we get the symmetry analysis playing an important role in mathematics, chemistry, engineering, classical mechanics, and quantum mechanics. When we come back to the Schrödinger equations, its study started around the 1970s when they started studying the linear Schrödinger equation by mathematician Neidler, Boyer, Miller, and in that case, normally the real valued potentials were considered, and the results normally in that case, they found the incomplete results because normally the phase shift were missing. In this case, the group classification of multidimensional linear Schrödinger equation with time-dependent and complex valued potentials have been investigated systematically by myself, by Popovich, and by Basarab since 2012. So the results in this case are summarized in the paper 2 and paper 3, which are in the reference. After that, the investigation of non-linear Schrödinger equations started now in 1976 again by Boyer, and we've cooperated with his co-authors. And then in that case, the exact solutions and the invariant solutions were obtained in 1+1 dimensional non-linear Schrödinger equations. From that time, many papers in the study of the non-linear Schrödinger equations were intensified from time to time, and most of the results was given by Popovich in 1+1 dimensional non-linear Schrödinger equations. So in multidimensional case, it is my results which is summarized in paper 4. In this talk, we are interested in the study of non-linear Schrödinger equations because non-linear Schrödinger equations appear in many areas of applications, such as theory of propagation of light in non-linear optical fibers, theory of Bose-Einstein conduction and plasma physics, the study of lasers, dissipative systems, nuclear physics, and so on. Secondly, admissible transformation of the most general class of generalized Schrödinger equations with variable mass and their subclasses are not known. So we need to investigate that class, and then we need to find their solution with respect to the symmetry point of us. Before going deep to the study, we need to define some terms or some concept. We need to define a class of differential equations. A class of differential equation will be a system of differential equation parameterized by arbitrary element, which we call here theta, where theta 1 up to theta k is a tuple of arbitrary element. The tuple x, which is equal to, given by the tuple x1 up to xn, stands for the independent variables, whereas u to the index p stand for the dependent variables together with their derivatives. Theta runs through the solution set S of an auxiliary system of differential equations, which is given by S xu theta equal to 0 and the inequalities which are given there, where both x and up are the independent variables and dependent variables, and sigma stand for tuple of function depending on x, up, and theta q. The set L theta, theta in S is called the class of differential equations and is defined by the parameterized form L theta, and the set S run by the arbitrary elements theta. If you want to give an example of the class of differential equation, we can give an example of this class of the evolution equation ut equal to f t of depending on tx, ux, and uxx. And in this case, f stands for the arbitrary element, and then the number of dependent variables is 1, which is equal to u, and the number, the highest derivative is equal to 2, is the second order evolution equation. The number of independent variables, they are 2, which are t and x, and then we have a single class of differential equation, k equal to 1, and the single arbitrary element theta, which is equal to f. The auxiliary system is given by the set S, which is given by the derivative of the arbitrary element with respect to the missing variables there. It is f of ut x, f ut t equal to 0. And the inequality system here will be given by f uxx different to 0, since we need to have this PDE to be defined to be evolution, a second order evolution equation. From this notation, L theta, one may note the above class as LF because it is a class with the arbitrary element F. So we substitute theta by F. Then we say that the group classification problem can be stated as follows. It is a comprehensive and systematic description of symmetry properties of the class LS together with their symmetries. That is what we call the group classification problem. And the group classification problem is solved when all inequivalent values of the arbitrary elements and their corresponding inequivalent symmetry extensions are obtained up to the equivalence relations. So it means that when we are solving the group classification of differential equations, we may use 3 categories of approach. There is infinitesimal method, the technique of equivalence transformation, and the classification of raw dimension subalgebras. These techniques sometimes may not work, and then we need to construct a theory which is relevant for our group classification. That is what we will do in our next presentation, because normally these 3 methods were combined, but they will not satisfy the solution of the group classification problem of Schrödinger equations we have. When we consider 2 systems of differential equation L theta and L theta tilde to be the 2 systems of the 2 systems of differential equations, then we denote the set of point transformation in the space of variables x and u by t of theta and theta tilde that map the system L theta to L theta tilde. Then an admissible transformation of the class LS will be a triple from the original arbitrary element, the transformed arbitrary element, and then the point transformation connecting those two systems. So it means that the admissible transformation here will be a triple consisting of two arbitrary elements, the target, the original arbitrary element, and the transformed one in S, such that the point transformation for a fixed arbitrary element is non-zero. And the point transformation phi should belong to the set of point transformation T of theta and theta tilde. We call the equivalence groupoid the set consisting of the all point transformations of such form theta, theta tilde, and phi, such that the transformed and the original arbitrary elements are in S, and phi is the point transformation. Then this admissible transformation has a groupoid structure, which means that normally we should have the property of the identity element which should be included in this group, and also the point transformation should be invertible, and also the composition hold for these two point transformations. When you have two admissible transformations, then the composition also is admissible transformations. And then the set of the all admissible transformation, call it the equivalence groupoid. While we're still having our problem, also we need to define the maximum point symmetry group and the common symmetry group. The maximum point symmetry group G theta of the system of differential equations for a fixed theta will be a group of transformation in the space of variables that preserves the solution set of the system. In this case, the set of point transformations is T, theta, and theta, since theta tilde is fixed and is equal to theta. Then the common part of the symmetry group, or the Kano group of the maximum point symmetry group, it will be the common intersection of all maximum point symmetry group of the system of differential equations. We will call the real algebra of the maximum point symmetry group the generator of one parameter subgroup of the maximum point symmetry group. And also we call the Kano invariance algebra the real algebra, which will be given by or generated by the generators of one parameter subgroup of the Kano group of the maximum point symmetry group. Which means this that here, if you want to do the group classification of differential equations, there are four terms we need to consider. The first one will be equivalence groupoid. The second one will be the symmetry group. The third one will be the common part, which is the Kano group. And also we need to define or to consider their generators, which are the real algebras of the maximum point, maximum real algebra, the Kano reinvariance algebra, and also the equivalence algebra. Once we have already understood those three concepts, we need also to define the equivalence transformation in the class of differential equations. So an equivalence transformation in the class of differential equations is a point transformation in the joint space of independent and dependent variables, their derivatives and arbitrary elements with the local coordinates x, u, p, theta that are projectable to the space of independent and dependent together with the derivatives of the dependent variables. And this projection should preserve the contact structure on the space with local coordinates x and up. An equivalence transformation also should map every system from the class of differential equations to a system from the same class. And then the correction of all such transformation will constitute what we call the equivalence group of the class of differential equations. Its infinitesimal part or the set of generators of one parameter subgroup of the equivalence group will be called the equivalence algebra. We have two notions of which are characterizing the properties of the class of differential equations. The first one is the normalization property. The second one is the semi-normalization property. A class of differential equation is said to be normalized in the usual sense if its equivalence groupoid is generated by the equivalence group, and then is said to be semi-normalized if the equivalence groupoid of this class can be generated by transformation from its equivalence group and also the maximum point symmetry group of equation from this class. So it means here that a class is semi-normalized when when an admissible transformation for this class is a composition of an equivalence transformations and a symmetry transformation. When we go deeper to the group classification of Schrödinger equations, we start with the wider class, generalized class of nonlinear Schrödinger equations of this form. Here we put the condition G to be non-zero in order to have the second order PD of class of Schrödinger equation, and then we study the transformational part and the transformational properties in this class. So it means that we want to look at the set of transformations which are mapping a class from a system from this class to the transformed one by using the technique of regroup analysis. And then what we will do, we will narrow this class into smaller classes or into subclasses which are better for studying. That is why normally restricting or putting conditions on this class, we will narrow this class by constraining the arbitrary element G, and then we come up to this class I psi t plus psi AA plus STX rho psi equal to 0 with these conditions. So we will denote this class by the class S of nonlinear Schrödinger equations, while we will denote this class with the capital letter N, the generalized class of nonlinear Schrödinger equations. So we will compute or we will find the equivalence groupoid for these classes, the equivalence groups, and also we will show that the delta class, this one, is normalized. Then, by specifying the value, the arbitrary element S in the class we have seen, by putting S equal to F rho psi, VTX psi, then we will get to this class called the class V, where the condition F rho should be non-zero and V is an arbitrary smooth complex valued potential depending on independent variables T and X. Then we use the equivalence group of this class, and then we find the equivalence groups corresponding to subclasses that will be singled out from this class by the conditions. This is the first condition, this is the second condition, and this is the third condition. And we will denote these classes by V prime, P0 and P lambda respectively, where sigma is a non-zero complex number, lambda is a non-zero real number, and they are referred to as, these classes V prime will be called the class of Schrödinger equation for general cases, the multidimensional classes for logarithmic modular nonlinearity, and then the last one will be the Schrödinger equation with power nonlinearity. Then, since solving this class is complicated, that is why we needed to split into these joint normalized subclasses V prime, P0, and P lambda, and then we study them separately. And then the result for this group classification will be the union of the all studied separate classes which will be obtained. That is here we say we solve each subclass separately and hence present all inequivalent values of the involved arbitrary element that admit properly symmetry extensions of the kernel invariance algebra. And then you solve these cases since you are in a multi-dimensional case for n equal to 2. So we start with the generalized class of Schrödinger equation, and then here we find its equivalence groupoid of this form, where capital T, capital X are the transformation in the independent variables. G is the transformed of the arbitrary element. Capital Psi also is the transformed of the dependent variables. So the transformation of the arbitrary element G and the F satisfies the following relations. And this is the class N of generalized nonlinear Schrödinger equations, whose equivalence groupoid is of this form, is not normalized due to the conditions we have here on this condition on psi. So since it is not normalized, its equivalence group Gn consists of non-degenerate point transformation in the space of independent variables and the arbitrary elements with capital T, X, A, psi, satisfying the first equation, so satisfying these first relations, and the components for the arbitrary elements are provided by the second and then the third equations. Since this class does not possess the good property, which is not normalized, we can narrow this class by taking into account by conditioning G star to be equal to minus G and G star to be non-equal to G, and then we obtain successfully the values of G and F up to setting G equal to 1 and make F not depending on psi A and psi star A, and then we come up to the class with arbitrary element F which is equal to STX rho psi, and then we come up to this class, which is very interesting now in the next. Then the class S now, whose specific form F, which is equal to S psi, is normalized and possesses the equivalence group of such form. Capital T, chi A, lambda, and sigma are arbitrary semi-Fourier functions of T with the condition T non-zero, then epsilon prime is equal to sine of TT, and the O here stand for an arbitrary constant n times n orthogonal matrix. So, restricting the value of S by setting S equal to this value, then we solve the group classification of the class V with this format. And this subclass now, which is a subclass of the bigger class S, is not normalized. So to study it, we need to partition it into three disjoint classes, V prime, P0, and P lambda, as I said, up, and these subclasses possess the normalization property. So, and then we study V prime, P0, and P lambda separately. So first of all, we fix non-linearity term F of rho in this subclass V prime of equations, then with this condition, and that the assumption that F is determined up to area multiplier and a complex conjugation. And then for the class P0, then we put the condition on F by F equal to sigma psi ln of rho. And then for the class P lambda, we restrict F to be this term, where sigma is a complex number, and then by putting the condition that the modulus of sigma should be equal to 1. With sigma 2 is greater or equal to 0. Here there is 0 which is missing, and the only arbitrary element to consider in these classes should be V. We recall that V also is a complex varied function depending on T and X. And then we study separately the class VF, P sigma, P delta 0 and P lambda 0 respectively, given by these conditions. So we will represent the group classification of the subclass VF and the other cases as they will be given in the paper 3, which is down. Now, we consider one subclass to show how the equivalence group will look like, and the symmetry algebra, how they will look like, and then we present the results for other classes because the methodology will be the same. The equivalence group of this class, of the class VF, which is up, this one, is constituted by the transformation 2. The transformation 2 is the transformation given in this class, where T will satisfy, where TT is equal to 1, and TT is equal to plus or minus 1 if F is a real valued function, and then the lambda is equal to 0. Then when we compute their infinitesimal generators, we obtain that the symmetry algebra of an equation from the class VF will consist of the vector fields of such form where D1 is equal to partial derivative with respect to T. G is a rotation operator with A different from B, and G also is given by this expression, and M will be given by also this expression. Chi A and sigma are real valued small function of T. C0 is a real constant, and the matrix kappa AB is an arbitrary real constant skew-symmetric matrix. So this matrix which is given there. Moreover, the coefficients of the above vector fields, so these coefficients, these D, G, J, and M, will satisfy what we call the classifying condition of this form. And then when you compute the Cannon invariance algebra, which will be the set of infinitesimal generators of the Cannon group, will be given by the operator N. For this class, we see that the maximum reinvariance algebra of the wider operators will be bounded by 7. So the maximum dimension will be less or equal to 7, whereas the maximum dimension of the intersection of the maximum reinvariance algebra together with this span will be less or equal to 5. When we go to the group classification, and then we do the investigation by investigating this class, we obtain the following theorem saying that the complete list of inequivalent symmetry extension and their corresponding potentials in this class are summarized in this paper. But since there are so many, we have 12 cases for this class. I tried to single out some cases to show you how the potentials will look like. So for the general case, where there is no extension, we will have the potential depending on independent variables. And when we have the space potential, where potential depends on the X only, we have this symmetry extension, and also we have the quadratic potential of such a form, and in that case the maximum reinvariance extension will be given by this span, where x pi 1 of t, x pi 2 of t is a fundamental set of solution of these systems. In a similar way, or in a similar procedure, the group classification list of subclass P delta 0, respectively with P lambda, give 13 families of potentials and 22 families of potentials and their corresponding symmetry extensions. Also, for the class P lambda 0, I will give some potentials and their inequivalent symmetry extensions to see how they will look like. And even also for this class, I will show you some of the potential inequivalent potentials together with their corresponding symmetry extensions. So for the class P lambda 0, it is the class defined by this system of differential equation, Schrödinger equation with nonlinearity of such form. We have certain cases, and then here I have identified 5 cases to show you how the potential will look like together with their symmetry extensions. Here the first case corresponds no extension. It means that this potential corresponds to the Kano invariance algebra, which is of this form. Here we have the potentials which are independent of the time, and then the symmetry extension is of such form. Here we have also the potentials which are depending on x, and also this is the symmetry extensions. And then the last one also is the complex potentials, which is given by this family of potential and can be, and the symmetry extension also will be given by the span of these operators, where this second order differential equation satisfies these relations, and chi p is also a solution of such form. Now, for this class we have here, for power nonlinearity, we have 23 cases given by inequivalent families of potential, and also we selected some for showing you how also the potential will look like, and also how the symmetry extension will look like. The first one will be no extension. Here we have the potential which are independent of the time, which will be given, which will give the symmetry extension of such form. And here we have also the quadratic potential, also which will be giving the symmetry extension of such form. And also we have also in this case the purely complex potentials, which will be given by this form, potential which is equal to I h of t. H of t is a smooth function depending on t, and then the symmetry extensions will be given by the span of these operators. When we are here, these potentials normally for nonlinear Schrödinger equations are very important. And here we have where the potential is reduced to 0, but we have 2 cases for this value of lambda, because lambda can be equal to 2 or lambda can be different to 2. And in both 2 cases, we should get the symmetry extension corresponding to each one of this value of lambda. And once the potential reduces to 0, it means that normally we will have our Schrödinger equation will be stopped here. We have no this term, and this is one where we have what we call the maximum re-extensions of higher dimension. If we check here, we have the dimension, the maximum higher dimension for our symmetry extensions. For the applications, as I was saying that Schrödinger equations are very relevant for the applications. These potentials we have found are relevant for any studying GPE, Gauss-Pitavetsky equation for quantum mechanics, and optical fibers, also nonlinear optics, fluid dynamics, and so on. Then, since you have split our class of differential equations into 3 cases, this is the last case, and then this is the previous case, the second case, and then this is the first case. And you have started separately these 3 cases. Each one gives the symmetry extensions together with their corresponding potentials. We need to get the final list of the group classification of this class, because this class was split into 3 subclasses, conditions by these conditions. So the group classification of this class will be given by the list of the group classification of those subclasses, which means the group classification of the class VF, lambda 0, and P, here it is P delta 0, here it is P lambda 0. And all of them also that list, which include around 38 potentials and 38 inequivalent symmetry extensions. All of them, they are summarized in this paper. For simplicity reference, those are the reference I have used. This is the last one. The last reference, this is the presentation I have done, because all results are summarized in this paper. These ones was the study of Schrödinger equations for linear case in 1 plus 1. And then this one was linear case in 1 plus 2. This was the good paper also, which was studying the nonlinear Schrödinger equation in 1 plus 1 dimension. So the multi-dimensional case, which completes the results in this paper, is this one.